Problems? Questions? I had a few questions during the break. One was exactly how does it work? It works in this way. Inductor, comparator, RS factor, flip-flop, clock. This is a clock that turns my switch on periodically, and this period of time is T switch. This frequency of these pulses is a switching frequency. How does it work exactly? Well, all this stuff is just a current source, a controlled current source, and this current source is controlled by V control. And V control is this voltage right here. And it comes out from an external loop, that is the voltage loop that senses the output voltage and tells to my control current source too much, too slow, too low, go up, go down, okay? We have two nested loops. One is a fast loop, fast non-linear loop, that is the current loop over here, and the other one is the slow voltage loop, the external loop, that is this one. You have one loop inside the other. And the internal loop is fast, the external loop is slow. And there is still a detail that I should add, so you avoid surprises if you work with this circuit. Let me just redraw it a little bit to the right. This is the voltage amplifier. This is the reference voltage. Something like this, something like this, and this comes from RS. Okay? Everything is clear over here? Well, there is just a detail, and the detail is, let's suppose, it's not the only way, but it's a common way to measure this current with a resistor. So, the voltage across this resistor has a value RS. The voltage across this resistor is what is compared over here. Here it's a single-ended input, here a voltage within a differential input. It's not a big deal. The problem is this. If I take this voltage and I compare with the error voltage, the control voltage that comes from the voltage amplifier, I have two opposite requirements. First requirement, I want these voltages to be large, so this amplifier works in a good linearity way, and if I have a large voltage over here, especially over here, I don't have so many problems with noise, with signal-to-noise ratio. On the other hand, if I have a large voltage over here, for example, this output voltage can swing from 0 to 5 volts, I need, I add times RS, that is 5 volts. And RS, 5 volts over RS, means 5 volts of loss on the output voltage. It means a large power dissipation on this resistor. So there are two opposite requirements. Stay high with these voltage levels because the signal-to-noise ratio is better. Stay low over here because otherwise your power dissipation is worse. And the standard, the practical standard is not defined officially, but the practical standard we find around is that IL times RS maximum is 1 volt. For new modern IC circuits, in some cases, if everything is inside, you can have less than 1 volt. You can have, for example, 0.25 volt, quarter of a volt, but let's say 1 volt. If you want to work with 1 volt over here, this op-amp cannot go down to 0, and if you limit the dynamic of this op-amp to from 0 to 1 volt, it's really too small. So what happens is that they want to increase the output voltage from this op-amp, not to 0, but a little bit higher, let's say from half a watt at least, and they want to have circuit designers, they want to have a voltage swing over here is at least 3 volts in order to improve by 10 dB the signal to ratio level. So what they do is here in between the error output amplifier, the output of the error amplifier, voltage error amplifier, and the input of the current comparator, they put a voltage divider R and 2R, voltage divider that divides this voltage by 3, by a factor of 3. So this sensing resistor can go from 0 to 1 volt, and this op-amp goes from 0 to 3 volts. So this is happy and this is happy. There is still one problem, and the one problem is that this amplifier cannot go down to 0. It has a minimum headroom voltage on the negative side. And so in some cases they put here a sort of a diode that could indicate the diode, basically they do something more sophisticated, in order to have a voltage drop here. It's like placing a battery like this. And until the output voltage here does not reach 0.7 volts at least, or 0.5 volts, whatever is this battery, it does not control, it does not ask for any current over here. This diode, this voltage shift offset is not important because any DC offset after an integrator is just divided by the integrator DC gain, and so it has no effect on the output voltage. This voltage division reduces by 10 dBs my loop gain. So when we do the calculation of the loop gain, if we consider this, we have to remember that we have one extra 10 dBs lost over here, factor of 3 lost over here. This is just a practical factor. It's not, there is nothing theoretical over here, over there. In some other cases, for more modern integrated circuits, you have here a direct connection, and between the sensing resistor input and the comparator, you have an amplifier by a factor of 3, so it's the same story. Okay? Let's see. Let's put here. Oh, forgot. In some cases, not in some cases, quite often, over here, on this input, you find a sort of a Zener diode with a maximum voltage of 1 volt. It's not a Zener. You cannot get a Zener diode that has 1 volt of Zener voltage. But you have something equivalent to a Zener diode like this. And this limits the maximum voltage over here. If you limit the maximum voltage over here, more than 1 volt you can get no matter what you do. It means that the maximum voltage over here can reach 1 volt. If the voltage at the non-inverting input tries to go higher than 1 volt because the current is ramping up, this in 50 nanoseconds open the switch and clamps, blocks, limits the limit is the right verb, the current to the inductor and to the switch. So if you limit this voltage, you limit the current to your inductor and to your switch. So let's see what are the advantages of this topology. 3 or 4 of them I already told you. Advantages.
That's not independent. No independent.
No?
We independent.
Oh. Audio susceptibility. Is almost 0. It's not really 0 because I made that approximation, I peak equals I average. But this is almost independent. Your colleague told me something more important, that is weighting independent. Weighting independent does not mean only audio susceptibility is 0. It's the loop gain independent from weight. This is the same story. One is the audio in small signal, the other one is large signal, basically, but still same story. Okay, more.
Cutoff frequency of the transfer function does depend from the loop.
And crossover independent from weight in and that is what I told you twice, and independent from up, low. So the crossover frequency is constant. I don't lose dynamic performances even if I move down, I change the load. The crossover frequency stays the same. A few more.
I can control more precisely the ripple, the output ripple.
Say again?
I can control more precisely the out ripple, the current ripple.
I can control more precisely the current ripple. No, because the current ripple, the inductor current ripple, is not dependent on the control mode. If you have an input voltage of 15 volts, an output voltage of 5 volts, and a buck converter in between, the duty cycle is 1/3. No matter if you are current mode, voltage mode, but you still have to have this duty cycle. And if you have this duty cycle, your current ripple is still the same. Current ripple does not depend on the control leg. Switch current is limited. Yeah, this is great. No matter what happens, the current cannot go above this 1 volt level, because if the current tries to go higher, the current comparator opens the switch immediately. So you have protection, switch protection. This is very important, I like it. Another advantage, does not seem to be a big advantage, but trust me, is a type 2 compensator. Don't tell me type 2 compensator is easier to design than a type 3 compensator. It's true, but you don't, I don't think you are scared by a type 3 compensator design. Type 2 compensator is a good thing because it's faster than a type 3 to recover from saturation. When you saturate the system, because for example you are asking for a very large current suddenly here in the output, this current cannot come from your inductance, because inductance has a slow DIDP, depends on the voltage. So this compensator sees the output voltage going down, starts to panic badly, and goes to the maximum. But it saturates, because the system is not responding. And it saturates, it means that these two capacitors charge to strange voltage, wrong voltage, and when you come back into linearity, you have to discharge these two capacitors to go back into linearity. If you implement digital integrator, the phenomenon is called wind up, because it goes to saturation, and also there are the anti-wind up systems for digital. Here you don't have the wind up. If you have a type 3 compensator, that is, you have one extra RC, this capacitor is critical for the saturation, the one that makes more damages. So if you don't have it, it's faster to recover from saturation. Not only, there is one extra advantage. And the one extra advantage is, at least one extra advantage, then there are more. So the one extra advantage is that going from CCM to DCM, your model, your transfer function between output voltage and V control does not change too much. Here in CCM, the transfer function between V naught and V control is something like this, gain whole 0. When you move to DCM, it stays the same. Numbers change, but no, the 0 stays exactly the same. The pole changes a little bit in frequency. When you move from here to here, the pole goes up. Not to refer to this one, but here is 1 over 2 pi RC. Here is 1 over 2 pi C times R parallel something else. But this R is larger than that. So this pole is going up because there is something going in parallel to R. But this is a low frequency because this R to go in DCM must be large. And this gain changes a little bit. But basically what you get is still the same shape and more or less the same numbers. It means that your compensator that you design over here with type 2 compensator that you designed for this condition is not exactly right, but it's still more or less okay for the DCM condition because the transfer function is the same, this frequency is the same, and these two change but not too much. So you can move from CCM to DCM without losing too much performance. In voltage mode, the story is completely different because in voltage mode, here you have two complex conjugate cores and 1 0, and you have a type 3 compensator. When you move to DCM, and every converter in CCM moves eventually in DCM if you remove the load. When you move to DCM, what happens is that the Buck DCM voltage model has this transfer function. And your type 3 compensator is not the right one. So you have a change of performances when you go to CCM to DCM, but not too much. You don't lose too much in performances. Okay? There are more of these advantages. For example, if you want to put in parallel two sources, two power sources, can you just connect them in parallel directly? No. It depends on the kind of power source. If you have two voltage sources, well, you cannot connect them directly in parallel unless they have the very same voltage. If you have two batteries, either they are the same and they have all their lives together, or you cannot connect the two batteries in parallel directly. Two batteries can be connected in series, but not in parallel. If my inductor becomes a current source because it's driven by the feedback as a current source, you can put in parallel many current sources. That's okay. You cannot put them in series, but in parallel is okay, current source. So you can have these converters in parallel very easily because they share automatically the current, because each converter has its own maximum current and they share evenly the currents. For example, for the multi-phase converter I told you about at the beginning when I told you about the variations on the buck converter, if you make a multi-phase buck converter, either it is very symmetrical, it means all the components are absolutely the same, especially with the parasitic resistances of the inductors, or the current is not sharing equally between the 2, 3, 4 stages. If you go current mode, they share, as a good friend, they share evenly the total current. Going CCM to DCM is okay. What advantages? Are there disadvantages? Yes, there are a few disadvantages, and the few disadvantages are, could be cost. because you have to sense IL. And sensing IL means you have to add a component at least, or maybe more than a component. Then the second disadvantage is noise sensitivity. Because, look to IL is something like this, and it's working with this IP. You control this IP and your IL ramps up till it reaches IP, comes down, ramps up and comes down. But this ripple is small because we are working in CCM, deep CCM. So if we have any noise, for example here, a small spike, a small noise that goes here, there are 2 millivolts here. Because this maximum voltage is maximum 1 volt, and this ripple is maximum, I don't know, I don't want to say maximum, but if this is 1 volt, probably this ripple is maximum 100 millivolts or less. So if there is a small volt, a small spike over here, it happens that as soon as this small spike, that is not a current jumping up, current cannot jump up to the inductance. It's because, for example, there is some noise coupled to the comparator. As soon as it jumps up, immediately the comparator senses, oh, overcurrent, switch it off, and immediately it switches the switch off. So current mode is noise sensitive because these 2 voltages, the peak voltage, the control voltage, and Rx times IL are very close, are always very close. And so if there is here, this phase, during this period of time, a small noise disturbance entering into the comparator, your comparator commands and opens the switch immediately. And better problem. Is it a big deal? No, but if you avoid it, it's not a big deal, because if you decrease your duty cycle, what happens? It happens that, and you keep decreasing many times the duty cycle, it happens that the output voltage starts to decrease. But there is the loop, the voltage loop, that says, oh, the output voltage is a little bit too low. I don't know why, but I ask for more current. So it tries to compensate, but it's not a good thing to do. And then there are 2 extra disadvantages, and one is that IL average is not equal to IP. There is a difference, there is an error. You see, this is IL, this is IP, and you see that the average current, IL average, is smaller than IP. So you command this current and you get something less. Is it a big deal? Well, if you look at the steady state condition, it's not a big deal, because if your current you provide to the load is a little bit too small, the output voltage will be too small, and the integrated voltage loop will increase the requested current, the IP value, in order to get exactly the output voltage. So these errors could be compensated by the voltage loop. But this is what prevents you to have a zero audio susceptibility. This is what prevents you to have fixed crossover frequency. Because, let's do an example. Consider, for example, that this is my IP and this is IL. That's all.